By now, we know that unlike simple linear regression, correlated data or longitudinal data calls for the modeling of both mean as well as the variance structure. Linear mixed model provides an opportunity to explicitly model the variance structure. In the previous session, we had learned what motivates us to use linear mixed model. In this session, we would be dealing with the formulation of linear mixed model. So, that means what is the model that is used as a linear mixed model? What are the parameters associated with the linear mixed model? What are the interpretation and significance of the parameters used in the model? The linear mixed model uses something called the random effect, and as we know, we cannot technically estimate random effects. We need to predict random effects. So, we would also learn something called the best linear unbiased predictor or the BLUBS, which is used to predict the random effects associated with a linear mixed model. Now, we start off with what is called the random intercept model. Consider that I have n individuals and n individuals have a random start, but the trajectory or the slope is same. So, then that can be modeled as yij is equal to beta naught I plus beta 1 Tij plus epsilon ij, where yij is the observation related to the ith individual at the jth time point. Beta naught I is the start of the ith individual or the intercept of the ith individual, and beta 1 is the slope. Note that beta 1 is same for all i's, that means all the individuals or the subjects has the same slope, but the intercept beta naught I contains the index I, meaning that the intercept is different for different subjects or individuals. Now, we can think in this way that this beta naught I consists of two objects or two terms. The first term is say beta naught, which represents the mean intercept of the population or the population level intercept, and then I can add a term b naught I, random in nature, which shows the variation of the ith individual from the population level intercept. So, putting b naught plus beta naught plus b naught I instead of beta naught I, what we get is yij is beta naught plus b naught I plus beta 1 Tij plus epsilon ij, meaning that yij has now basically two components. One is the fixed component, that is beta naught plus beta 1 Tij. This means that there is a at the time point Tij, there is a population level value which is equal to beta naught plus beta 1 Tij. The effect of the ith individual is coming from the term b naught I. So, b naught I is nothing but the random intercept and epsilon ij, which is the random error. So, the final formulation becomes like yij equal to beta naught plus b naught I plus beta 1 Tij plus epsilon ij, where b naught I follows normal 0 sigma square naught and epsilon ij follows normal 0 sigma square, with the assumption that the random effects b naught I and epsilon ij are independent. We can have a similar explanation for the random slope model. So here what we can think is that all the individuals have more or less the same intercept, but the slopes are different for each individual. So that means I can say Yij is equal to beta naught plus beta 1 I Tij plus epsilon ij, and note the use of the suffix I in beta 1. So that means beta 1 I means the ith subject specific slope, and the ith subject specific slope can be decomposed into two parts. One part is the one part is the population level slope, and one part is the variation of the from the population level slope of the ith individual, which is denoted by b1i, and b1i is assumed to be a random variable following normal 0 sigma square 1, and so the full model now becomes Yij is equal to beta naught plus beta 1 Tij plus b1i Tij plus epsilon ij, and b1i follows normal 0 sigma 1 square, epsilon ij follows normal 0 sigma square independently and identically, and b1i and epsilon ij are assumed to be independent. Now we can combine both the ideas of a random intercept and a random slope model to get what is called a random intercept random slope model. So here what happens is, for every individual there is a subject specific intercept and a subject specific slope. At the second level, what we do is the subject specific intercept is broken into population level intercept plus a individual variation in the intercept due to the ith subject, and similar explanation holds for subject specific slope, that is we have a population level slope and a variation due to the ith subject. Now the variation due to the ith subjects in both the intercept and the slope are assumed to be normal, so jointly they follow a multivariate normal with 0 mean vector, and the variance is sigma naught square, sigma 1 square at the diagonals, and sigma 0 1 sigma 1 0 at the off diagonals. Now what happens is, sigma 0 1 sigma 1 0 is nothing but covariance of b0 b1, where b0 is the vector of individual effects or the random effects of the intercept, and b1 is the vector of the random effects of the slope, and epsilon ij is again IID normal 0 sigma square with the assumption that bi is independent of epsilon ij. So the final model now becomes is Yij equal to beta naught plus beta 1 Tij, and that is the population level trajectory. And we have an individual level trajectory which is b naught I plus b1 I Tij, which is the random effects level or the subject specific contribution of the ith variable or ith subject, and epsilon ij is the random effect. So now we are in a position to define a linear mixed model. The linear mixed model is defined as yi equal to xi beta plus zi bi plus epsilon. Note that here xi is called the design matrix of fixed effects and zi is called the design matrix of random effects, and epsilon I are the random here. So we assume that yi is a ni cross 1 response vector, xi is a ni cross p design matrix of fixed effects already told, and zi is a ni cross matrix design matrix of random effects. So what are the parameters here? We have basically two parameters. So beta, different parameters. One is the fixed effect parameters and one is the random effects parameter. So here beta represents the fixed effect parameters, which is a p cross 1 vector of fixed effects regression coefficient. So for example, in the random intercept random slope model, beta naught and beta 1 were the fixed effect regressions. And then we have bi, which is a q cross 1 vector of random effects or subject specific effects. Now again in the random intercept random slope model, b01 and b0i and b1i were the bi coefficients. So there both were p equal to q equal to 2 in a random intercept random slope model. The assumption is that bi follows IID normal 0 D, and epsilon I as usual is the error vector with epsilon I following normal 0 sigma. Here I have mentioned it as sigma square I, but in general it can take any positive definite matrix called sigma. So epsilon I can be normal 0 sigma. A special case is normal 0 sigma square I. Now epsilon I and Bi are independent. So using this notation we can say that yi follows a multivariate normal distribution with mean xi beta and variance v alpha, where v alpha is zi d zi transpose plus sigma square ii, and alpha is the variance component parameter. So all the parameters that are involved in the variance component is combinedly called alpha. So what are the features? Now D being a variance covariance matrix should be symmetric and positive definite. The columns of Z are typically a subset of Xi. Now we see in random intercept model the Zi is nothing but a column of 1. In random slope model, Zi is nothing but a column of the time points, observed time points, that is Ti1, Ti2, Tin or Tik. And in a random intercept, random slope model, Zi is nothing but Xi, where Xi is the design matrix of fixed effect having an intercept and time. The conditional mean of yi given the random effects Bi is expectation of yi given Bi, and that is nothing but xi beta plus zi Bi. So conditional on Bi, the mean of yi is xi beta plus zi Bi. The marginal mean is obtained by taking an expectation of the conditional mean. So expectation of xi beta plus zi Bi, which is xi beta plus zi expectation of Bi, and it comes out to be xi beta because expectation of Bi is 0. Similarly, the conditional variance of yi is covariance of yi given Bi, and conditional on Bi, the only variability we assume is through epsilon I. That means if Bi is known, the only variability present in the data is due to epsilon I. So that is covariance of epsilon I equal to lambda, or here we have taken sigma square I, so that's sigma square I. But covariance of yi, the unconditional or the marginal variance of yi is zi d zi transpose plus sigma square I. Now if we are to test null hypothesis regarding the fixed effect parameters, that's the betas, we can employ an F test. For nested models with different mean structures, likelihood ratio test can be used to test hypotheses involving fixed effects. Likelihood ratio tests can also be used to compare nested models with different variance parameters, but the nesting should be at the level of the variance parameter. That means I can always compare a random intercept and a random intercept random slope model using a likelihood ratio test. But to compare a random intercept model and a random slope model where there is no nesting in the variance parameters, I cannot use a likelihood ratio test. In the next session, we would see an example of this when we are practically doing or fitting linear mixed model in R. But in situations like that, we can use model comparison criteria like the Akaike information criteria or the Bayesian information criteria and compare non-nested models. The idea of this model comparison AIC and BIC is that smaller is the AIC or BIC, better is the model. But it should be noted that they are not formal test of significance. They can indicate or they can compare based on information or log likelihood that which model is better than other given the data, but they are not a formal test of significance. Also, the random effects Bi are random variables because they are samples from a normal distribution is what we have assumed. So, we cannot estimate Bi's, rather we predict Bi. Now, in the context of predicting Bi, we introduce something called the best linear unbiased predictor. Now, the best linear unbiased predictor is defined as follows. For any arbitrary vector S and T, the best linear unbiased predictor predictor or bluff as it is popularly called, B hat and beta hat minimizes the prediction error. That is, expectation of S transpose X beta hat plus T transpose Z B hat minus S transpose X beta plus T transpose Z B. So, we are searching for the quantity beta hat and B hat which minimizes the form as I just said, subject to the unbiasedness condition, that is, expectation of S transpose X beta hat plus T transpose Z B hat equal to S transpose X beta plus T transpose Z B. Now, on solving this equation, the bluff of beta comes out to be X transpose V inverse X, X transpose V inverse Y, and immediately we recall that this is nothing but the WLS estimator. Also, we know that WLS estimator is a best linear unbiased estimator of beta. So, the bluff of beta is nothing but the blue of beta and is identical to the weighted least square estimator. However, the bluff for B comes out to be dz transpose V inverse Y minus X beta. Now, bluff of beta and B involves the unknown V's and D. So, what we can do is we can have the ML or REML estimates of V hat and D hat, and then we can plug in. So, now the bluff of B becomes dz transpose V hat inverse Y minus X beta hat. So, that is so the bluff of B becomes D hat Z transpose V hat inverse Y minus X beta hat, and this becomes nothing but the estimated bluff or E bluff. Now, we can use beta hat and B hat and predict the YIs or the observed responses. So, YI hat is nothing but Xi beta hat plus Zi B hat, so where Yi hat is the predicted value of Yi. Now, putting the best linear unbiased predictor for B hat, we get Xi beta hat plus Zi d Zi transpose V inverse Y minus Xi beta hat, and then on some simple algebraic manipulations, we can come into the form like Yi hat is equal to sigma I Vi inverse Xi beta hat plus Ini minus sigma I Vi inverse Yi, where sigma I is nothing but the residual variance, which is Vi minus Zi d Zi transpose. So, if we can see here, Yi hat is nothing but say A sig Xi beta hat plus B Yi, where A is sigma I Vi inverse and B is I minus sigma I Vi inverse. So, we see that Yi hat is nothing but a weighted average of population mean and observed data. In this session, we have learned how to express a linear mixed model. What is the model formulation and what is the meaning and the significance of the parameters associated with the linear mixed effects model. In the next session, we would be specifically taking the orthodont data, and then we would be using various types of linear mixed models to fit the data. The entire fitting would be performed in the NLME package in R. So, the next session would act like a practical to what we have learned in this session.